In this video, we're going to talk about Markownikov's rule and addition reactions and electrophilic addition. So here we have all our addition reactions, which we're going to talk about in the first year of your A levels. Okay, and we can see here we've got hydrogenation at the top. Remember, this here really important. You remember these conditions: catalyst nickel, 150 degrees. Okay. And that's it, reducing with hydrogen. Then we've got bromination, so we go to this colourless. The bromine decolorizes because once you make it into this product here, that is colourless, and that's the test for alkenes. If it goes colourless, the bromine goes colourless, it's an alkene. Test for unsaturated compounds. And then we have here, same thing but with chlorination, and then same thing here with HBr, producing the mono substituted version with that H and that Br. Now, these are all electrophilic addition mechanisms. So we're going to go over what that mechanism is. So here we have a picture. If you watched one of the earlier videos or done it in class, we've got a picture of an alkene in terms of the bonds and the orbitals. So we can see here we've got the sigma bond in the center, and then on the outside we've got this pi bond above and below the plane, important words, okay? And those electrons are localized between the two carbons, one carbon being here and another carbon being there. So they are localized, and that means that's an area of high electron density. So high electron density, so it's really important. And it's localized, as I said. Now I'm going to show you a little graphic here, and I want you to look carefully down here because the bromine's going to come in. And that bromine's going to come in has 2 electrons on it. Those electrons, when they get close to this area of high electron density, are going to repel because the electrons in here, in this pi bond, okay, are at negative, and then the electrons in the Br2 are also negative. So as it comes in, we can see it coming in. Look at the position of these electrons. They're just moving slowly but surely away because they're being repelled by these electrons in here. This only happens if the bromine goes towards the alkene at this direction. Most bromines will go off in random directions, but some of them will go straight on. And you'll see this repulsion here. Now, because the electrons are further down this end, this becomes delta minus, and that becomes delta plus. And this becomes your electrophile. So as we're writing it out, the halogen moves closer to the area of high electron density. The electrons are repelled. They cause the dipole, which we've got here. This generates your electrophile. Just to remind you, the electrophile accepts a pair of electrons to form a dative covalent bond. Now if we look at this and we see how this is worked, normally, we'll draw this again in another slide as well, but the electrons are coming out from here and going to go towards that bromine. Notice the arrow goes to the atom. Always really important when you do mechanism, it goes to the atom, not to the plus. Okay, and then here, because there's too many bonds between the bromine now, because this is going to form a bond to the bromine, that means the bromine have 2 bonds, so I need to get rid of the bond and I take the electrons out, okay, and I put them onto the end. And that is essentially the first step of your electrophilic addition mechanism. But we'll go through the entire electrophilic mechanism next. Now we're going to show you the mechanism of electrophilic addition using a permanent dipole, and we're going to use HBr. A permanent dipole exists in hydrogen halides, so HBr, HCl for example. The pi bond breaks like we've shown in the previous slide, okay, and you get heterolytic fission. Heterolytic fission creates a positive and a negative ion. A pair of electrons moves towards the delta positive hydrogen, which is our electrophile because it accepts that pair of electrons to form a dative covalent bond. The negative ion lone pair, or the negative charge, because we're going to show it with a negative charge today, moves towards the positive carbocation. That's a positive species made of carbon, forming a dative covalent bond. So let's show you how this works and do it with ethene. So we're going to do it here with ethene, and there is your ethene. So we've got an unsaturated compound. We're going to do electrophilic addition. Now, from there, the HBr has a permanent dipole. So it has a permanent dipole. That means that the electrons are closer to the bromine than they are to the hydrogen. They're closer because the bromine's more electronegative. Now, if that is the case, okay, with those electrons being closer to the bromine, we can get a delta negative and a delta positive charge on here. our delta positive, then becomes our delta positive hydrogen for this mechanism. So from there, we have our high electron density, which we explained in the previous slide, okay, here. Those are electrons, they're negative, so they're attracted to a positive. So those electrons move between this carbon and this hydrogen. And you can tell that because the direction at which the arrow comes from is where the atom is going to bond to. So it's coming from this direction, which means that hydrogen is going to bond to that carbon. Now, if that is the case, let's draw our carbocation. So we know that hydrogen is going to go on that carbon. So let's put the hydrogens on. So notice that this carbon now has 3 instead of 2, because it's got that hydrogen. And we draw the other hydrogens on the next one. Now the clever bit here is this. There are 2 electrons in this bond here. So there's 2 electrons in the bond here. So I've got 2 electrons. Okay, those 2 electrons are now here. Which means essentially 1 electron is from that carbon, the other electron is from this carbon. That means this carbon here has lost its electron because its electron is now between this carbon and this hydrogen. So that's why we can draw a plus, because it's lost an electron. Now if we go back up here, we're going to prove how you get the Br minus. So if you look here, this hydrogen can only ever have 1 bond. So 1 bond. So this is creating a bond with the hydrogen, which is down here. Okay, which means this hydrogen would have 2 bonds. I don't want it to have 2 bonds, it can only have 1. So I need to get rid of a bond. A way of getting rid of a bond is to take the electrons out of a bond and place it onto an electronegative element, like we've done here. So that's a classic way of doing it. Now, if that is the case, we have our Br and we have the minus. Now we can put the lone pair of electrons on if we want, because there's a pair of electrons. Okay, we can either do it as a dot and a cross, or we can just keep it simple, because most of the time you'll just see it as a couple of dots. And when you're doing the next part, because a minus is attracted to a plus, you can either go from the minus, because the minus is there because this bromine's got an extra electron. So this bromine's got an extra electron because it's got the hydrogen's electron. Okay, you can either come from the lone pair or you can come from the negative charge. To be simple, I'll come from the negative charge. And notice the arrows are going towards the atom. They're not going towards the positive charge. The positive charge is inside the atom, so the arrow should go to the atom, not the charge, okay? And this goes to the atom, this goes to the atom. Now from that point, we then draw it all, because this is then going to donate the electrons there and form a dative covalent bond there. So there you have your final mono-substituted ethane, so bromoethane. And that's been done using permanent dipole, which is here. That pi bond breaks, there's the pi bond breaking. Okay, pair of electrons moves towards the delta positive hydrogen. Okay, the negative ion lone pair. So this is the lone pair, but we decided to take it from the negative because it was simple and easy, but you can take it from the lone pair. Moves towards the positive carbocation, which is this, and this is a primary carbocation because it has 1 group attached to this positively charged carbon. And we'll talk about that in a bit more detail next. Okay, and that forms this dative covalent bond between here, and you get your mono-substituted bromine. So now we're going to go through Markownikov's rule and the electrophilic addition to unsymmetrical alkenes. So there's 2 ways of looking at this rule. The first one is when the compound HX, X being a halogen, because it's usually HCl or HBr, is added to an unsymmetrical alkene. We're going to do propene, and the hydrogen becomes attached to the carbon with the most hydrogens attached to it. So the hydrogen out of here becomes attached to the carbon with the most hydrogens attached to it. I find that explanation harder to follow. This one I prefer. The negative ion becomes attached to the carbon with the most alkyl groups attached to it. And we'll explain why that works in a second. Let's put this to the side, okay, and then look at a reaction. So a reaction could be propene plus hydrogen bromide, and then you'll get 2 options of products, 2 bromopropane or 1 bromopropane. Okay, so I could go position number 1 or position number 2. Now, if this is the case, let's draw it, okay, and feel free to draw it yourself. Stop the video, draw it yourself. If you look here, there's your 1 bromo, and there's your 2 bromo. Now, why does this work? Okay, this works because, think of it here, the negative ion becomes attached to the carbon with the most alkyl groups attached to it. So if you look here, the negative ion is the bromide ion. So in our mechanism we did before, it's the bromide ion. Bromide ion gets attached to this carbon right here. This carbon has 1, 2 alkyl groups. This bromine gets attached to this carbon right here. It has 1 alkyl group. That's it. So this has 1 alkyl group, this has 2. So it says here the negative ion becomes attached to the carbon with the most alkyl groups, which is definitely that one. So this 2-bromopropane is going to be the major product. Now, let's talk about the stability of the carbocation and why that works. So I've got propene. Let's draw it here. We know that our propene is going to be like this, and you can draw the mechanism out. You don't need to wait for me to do it. You draw the mechanism out and look at the intermediates as well. Okay, so we know that the HBr is going to come in, and then we know our HBr is going to come in there. Okay, so it's going to come in and attack this. We know that we can either have the arrow is going to come out, and the arrow is going to come out. Okay, we've got that. Well, the H can go on that one or that one. Okay, so let's draw both. So here we go, and here we go. So think of the intermediates. You can draw this. Stop the video, draw this. Okay? Now, if that's the case, we can have the plus here, or we can have the plus here. The plus here or the plus here. Okay, that means the hydrogen has gone on to this one, or the hydrogen has gone on to this one. Okay. Now, if that's the case, we have Br minus, we have Br minus. Okay, and then arrow comes in, then the arrow comes in, and we've got our 2 mechanisms. So our 2 mechanisms are done. Now, if you're not sure about this, I've drawn it skeletally. Okay, so it takes less time to do, otherwise I'm drawing all the hydrogens out. Draw it in displayed form, if you're not sure, and you'll see this. Now, if we then go to the next part, okay, we will then, from this, get Br, and then Br. Okay, so we have got, from here, we have got 2 bromo, 1 bromo, through that intermediate and through that intermediate. Right, if that is the case, and we look here, we can say, right, which one is the most stable intermediate? So that's what we need to talk about, and this is about answering the questions fully. Markownikov's rule said that the one with the most alkyl groups, okay, the negative ion will attach to the one with the most alkyl groups. So we have 1 alkyl group here and 1 alkyl group here, and they're attached to this carbocation positive charge. So that's 2. This only has 1. So 1. So this is known as a secondary, okay, as in 2, and this is known as a primary. Okay, and that is a secondary carbocation, and that is a primary carbocation. Okay, so we've got secondary and we've got a primary carbocation. Now what actually happens is the electrons are pushed ever so slightly towards this positive. And the electrons are pushed ever so slightly towards this positive as well, just because that's alkyl groups. There is a term called electropositive. They just slightly push electrons away from themselves. And if that is the case, this cancels out this positive charge just a little bit, and this cancels out this positive charge. But if there's more alkyl groups, it cancels out the positive charge more, which means this is more stable. Okay, so that is more stable because it's pushing more electrons towards this positive charge, so more stable. Now, I'm going to draw a little bit of a diagram for you just to show what that would mean. So here's an energy diagram, so let's just call this energy. okay, and call this progress. If that is the case, imagine you had an energy diagram. Imagine this was exothermic, for example. And this is your reactants, and this is your product. So in this case, your reactants is going to be this, okay, and your product's going to be that. Now, if that's the case, and we look here, your intermediate is up here. So this is your intermediate. So I'm going to call this intermediate 1, and I'm going to call this intermediate 2. Okay, so think about it right now. I want you to think, draw this out, and think to yourself, which one is going to be more stable? Well, the first one, that's going to be more stable. What does more stable mean? More stable means it has a lower energy, okay? If this is your intermediate, and one has lower energy than the other, this one has a higher energy, this one has a lower energy, so we could draw two reactions going on here. And this one would be, we've got I2, because it's a higher, the intermediate has a higher energy because it's less stable, okay? And this is your intermediate 1, which is this one, which has a lower energy, okay, because it's more stable. And this is where you get to understand it. You don't need this to write out the answer for the exam. We'll talk about that at the end of this slide, but this really makes you understand it. If this is the case, your activation energy for this, the amount of energy it takes to react, is small, or your activation energy for this is large. Okay, is all the way up there. So you can either have that much activation energy for number 2 or that much activation energy for number 1. Okay? Now, the one that has the lowest activation energy takes the less energy to react, which means the rate of reaction is going to be higher. And that is why the rate of reaction of this one is higher than this one, which is why this is the major and this is the minor product. But what are you going to say in an exam? In an exam, you're going to say, first of all, you have to say this is a secondary carbocation. You have to say it's more stable. And then you have to say what the major product is. So the major product is this. So if that is the case, we've got the mechanism, we've shown you the stability of the two intermediates, we've shown you the major and minor products, and give you a little bit of information of why that actually works. Now, the last thing I want to say is, now put this together in a little bit more detail. Think about this. There are primary carbocations, there are secondary, but there is also tertiary. Okay, so you might have it when there's 3 groups attached to it, and that's going to be even more stable than a secondary carbocation. Okay, the tertiary is more stable than the secondary, and the secondary is more stable than the primary. So if I had a tertiary option here, that would be the major product. And that is how you use Markovnikov's rule. So we simplified this down a bit, taken the mechanism out at the start, and just tried to show you the different steps. The first step with the HBr added to it, very, very slow compared to these 2 steps. So this is very, very fast, okay, and this is very, very slow, which is why this is the major product. Now, if we then go through it again, just again try and keep it really simple, the reason it is because of this activation energy. You can see the intermediate, the primary carbocation, has a higher energy, and therefore the activation energy is much higher. And then the secondary carbocation has a lower energy, and therefore activation energy is a lot lower. So with the less stable one, it's higher energy, higher activation energy lowers the rate. Okay, which means the reaction goes really slow. The more stable carbocation, lower energy, lower activation energy, and higher rate, which goes really fast, which is why your 2-bromo is your major product. It's much easier to form that secondary carbocation, it's more energetically stable, and therefore your activation energy will be lower. Now, let's do an exam style question, but let's try and show you how simple it truly is, because it is actually really, really simple. The negative ion becomes attached to the carbon with the most alkyl groups attached to it. So let's think of something like cyclohexene. So there's methyl cyclohexene. We know that that can create, okay, 2 different intermediates. All right, so the intermediate can be this, okay, where the plus is going to be here, or the intermediate can be here, and the plus would be down here. So that's just basically the H going on here or the H going on here, okay? So there's our two intermediates, right? So all you have to do is think of your two intermediates when you're posing the question. So which is the major product of this reacting with HCl in this case? Okay, what's the major product of that reacting with that? I'm going to have two intermediates. Now those two intermediates are going to have either Cl going in there or the Cl minus going in there. So that would create the chlorine on here, and this would create the chlorine down here. Now, if that is the case, which one's more stable? So the most stable one is going to be the one with the most alkyl groups. So this has a group coming here, group here, and a group here. So this is called a tertiary carbocation. This one has a group coming towards a positive charge here and a group coming towards a positive charge here, which means it would be a secondary carbocation. So these are the key things you need to write. You need to identify the carbocation, okay, and then say its stability. Well, the tertiary is more stable. Okay, that's less stable. And therefore this one is our major product. So think of it as 1, 2, 3. Okay, so 1, 2, 3 marks. And that is how complicated any of the exam questions will be. It'll just be, here's a compound, what is your major product and why? 3 marks.